Modern precision agriculture relies heavily on cloud computing, but out in remote fields, cellular signals drop. When a tractor enters a dead zone, cloud-dependent intelligence tools instantly fail, stalling critical operations. To solve this, we are going to build a workflow that generates an AI-driven agricultural prescription file directly to hardware using a simple USB drive. Completing this process ensures your planting and fertilizing schedules are never delayed by a lost connection. Before we begin routing data, ensure your system is running QGIS version 4.0.0 or higher and the Leaf Engines plugin version 1.0.4. Step 1 is establishing our geographic foundation. Navigate to the Web Feature Service, or WFS, connection dialog in QGIS. Here, link a compliant government data source, like the USDA in the US, or the PDK-BRP for Dutch crop parcels. Bringing these layers into your project populates the map with raw, unenriched geometric boundaries. Before moving forward, you must physically click to highlight your exact field polygon. This deliberate selection is strictly necessary. The AI requires a defined, constrained spatial boundary to pull accurate environmental metrics for your specific land. Locking on to these verified coordinates anchors the project to reality, ensuring the AI analyzes your specific acreage rather than hallucinating data or applying intelligence to a neighboring farm. With the boundary set, open the Leaf Engines side panel to pull overlapping intelligence. Start on the Soil tab and query the USDA database to extract metrics like pH and texture for your selected shape. Next, move to the Water tab to retrieve EPA water quality indicators. Then, switch to the Impact tab and run the environmental assessment to evaluate regional risks like runoff potential. Under the Carbon tab, input your field-specific variables. For example, setting your current organic matter level allows the system to calculate estimated carbon credit feasibility for that exact acreage. Navigate to the Final tab. Specify your planned crop type, such as corn, and hit Get Recommendations. This prompts the AI to synthesize all this gathered data into actionable planting advice. Here is how these separate queries are physically interacting with your map. The distinct soil, water, and climate databases are mathematically compressed and joined directly into your single highlighted boundary. Open the layer's attribute table. You will see that the analysis has permanently attached new columns, like specific risk scores and suitability rankings, directly to your geometry. By forcing separate government databases to merge onto one strict geographic footprint, we expose intersecting operational risks that isolated spreadsheets typically hide. Now we sever reliance on the cloud. Go to Layer 3 of the plugin and enable the On-Device Mode toggle. Note that this initial activation requires downloading a 600 megabyte local Gemma AI model to your hardware. You must complete this initial caching step while you are still at the office on a stable Wi-Fi connection. Once cached, a local optimization called TurboQuant takes over. This allows the AI to process complex, multivariable spatial queries in under 5 seconds, entirely offline. Disconnecting from the network guarantees operational continuity for teams working in extreme dead zones. It also ensures absolute data privacy for enterprise clients whose workflows mandate that sensitive analysis never leaves the local machine. To translate this digital analysis into hardware instructions, open the Export dialog within the plugin interface. If you are running modern tractor monitors, select the Isobus XML file format. For those operating older legacy controllers, choose the Zoned Shapefile option. Generate the file, locate it in your local directory, and drag it straight onto a portable USB drive. These standardized formats convert your spatial analysis into direct physical instructions for the machinery, detailing exactly where to alter variable rate seed and fertilizer deployment. Relying on strict export standards removes the risk of manual data entry errors. It guarantees that the physical machinery in the field executes exactly what the AI prescribed. We have moved from raw geometry to fused environmental data, processed the analysis entirely offline, and formatted the results for immediate field deployment. Your immediate next step is to take that USB drive and plug it into a physical tractor cab or a virtual display environment to verify the mapping coordinates. If you are a commercial operator looking to deploy this offline architecture across an entire fleet, reach out via the partnership team link below to discuss scaling. By integrating local AI directly with physical hardware, QGIS functions as a secure command center, the connective tissue between digital intelligence and physical execution.